Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we are going to be discussing about fluid at rest, but we've divided this topic into two. So today we'll be dealing with fluid at rest part 1, while in subsequent video we'll deal with fluid at rest part 2. So relax, do not go anywhere, and we'll be right back. Welcome back to my school YouTube channel. In today's video, we are going to be dealing with fluid at rest part 1. And in fluid at rest part 1, basically we are going to be discussing about the concept of volume, density, and relative density. So before we begin with our lesson, as usual, let's quickly run through the objective for today's lesson. So at the end of this lesson, students should be able to A, define density and state each unit, B, describe how to determine density, C, define relative density, D, describe how to determine the relative density of solids and liquid, E, identify the forces acting on a body completely immersed in a liquid and establish the condition for the body to float on the liquid. So let's begin with our lesson. So the concept of volume, density, and relative density are essential when discussing fluid at rest. So we are going to be discussing this concept one after the other to foster better understanding. So let's begin with the concept of volume. So volume is defined as the amount of space occupied by a substance or an object. Volume is usually measured in cubic meters, okay, for solid and liquid. Okay, so to calculate the volume of regular shaped object, we use specific formula. For example, for us to calculate the volume of a cuboid, we use length times breadth times height. Okay, so let's move over to the concept of density. So we define density of a substance as its mass per unit volume. So mathematically, density is equals to mass over volume. Okay, and density is usually represented with a Greek letter, okay, called rho. So this is the symbol of density, and this symbol is called rho. Okay, so density is also equal to mass over volume. Okay, where m stands for mass and v stands for volume. So where this symbol here called rho, okay, represent density, although the SI unit of density is kilogram per meter cube, right? But in laboratory works, results may be obtained in gram per centimeter cube. So to change a density from gram per centimeter cube to kilogram per meter cube, we simply multiply the gram per centimeter cube density by 1000. Okay, so that is how we change from gram per centimeter cube to kilogram per meter cube by simply multiplying the density given to us in gram per centimeter cube by 1000, okay, in order to convert it to kilogram per meter cube density. So for example, if we are to convert the density of 0.2 gram per centimeter cube, okay, to its SI unit, which is kilogram per meter cube, we simply multiply by 1000. So in kilogram per meter cube density will now be equals to 0.2 times 1000, and that will be equals to 0.2 times 10 raised to the power 3 kilogram per meter cube. Okay, so the density of water is about 1 gram per centimeter cube or 1000 kilogram per meter cube. So let's move to the next slide. So here are the density of some substances. Okay, so but the ones that are worth taking note of is that of water and mercury. Okay, so these densities are given in gram per centimeter cube. Okay, so for mercury is 13.6 times 10 raised to the power 3. Okay, and the density is in kilogram per meter cube. Take note of that. While that of water is 1.0 times 10 raised to the power 3 kilogram per meter cube. Okay, while the rest are for the density of the other substances that are listed, like gold, like lead, like brass, iron, aluminium, glass, water, paraffin, oil, wood, petrol, air, etc. So let's move to the next slide. Okay, so let's talk about relative density, right? So since water is the most common substance and has a density of 1000 kilogram per meter cube, it is convenient to use it as a standard for comparing the density of other substances. Okay, that being said, the relative density of a substance is defined as follows. Now, what you must take note of is that relative density is a ratio. Okay, so we can define relative density as the ratio of the density of the substance to the density of water, or the ratio of the mass of a substance to the mass of an equal volume of water, or we can also define it as the ratio of the weight of a substance to the weight of equal volume of water. So mathematically, relative density is expressed as follows. Okay, density of the substance all over density of water, or mass of substance all over mass of equal volume of water, or weight of substance all over weight of equal volume of water. But in subsequent slides, you still see other formulas that we can use to calculate the relative density of substances. Okay, so relative density is also known as specific gravity. So take note of that, right? So sometimes they can use the word specific gravity. What they are saying in essence is relative density. So one thing you must know about relative density is that relative density has no unit. Okay, for example, the relative density of mercury is 13.6. Remember that the relative density of mercury, okay, if we are referring to the SI unit, is 13.6 times 10 raised to power 3, right, kilogram per meter cube. You get? So the only difference is just to remove the unit. So relative density has no unit. Okay, that is why the relative density of mercury is 13.6, right, and that of water we can say is 1, okay, or we can say is 1000, right? So let's move to the next slide. So here we are going to be discussing how to determine the density of solid by direct method. Now, for a regular solid, now when we say regular solid, we mean those solids that we can give a name to their shape. Okay, for example, if we talk about a block of wood, right, we can say that block of wood is in the form of a cube. Okay, that's what we mean by a regular solid. So regular solids are those solids that we can give a name, or we can name them by shape. Okay, so for a regular solid, the volume can be easily found by measuring its dimension. Like I said earlier on, that we can use specific formulas, okay, to find their volume. Okay, so for a regular solid, the volume can be easily found by measuring its dimension, right? That is, we measure the length, measure the breadth, measure the height, okay, in case of a cuboid, right? So the mass can be obtained by direct weighing. Now we can use a beam balance to measure the mass of the solid, right? Thus, its density can be calculated, and this we can easily use the direct formula to calculate it, which is density is equal to mass over volume. So let's see an example. Find the density of the material of a cylinder of base radius r is equal to 0.1 meter and height h is equal to 0.5 meter. If the mass of the cylinder is 44 kg, which is 44 kilogram, what kind of material is the drum likely made of? What kind of material is the drum likely made of? So here is the solution. Okay, so I just did this on the screen because it's quite easy. So density is equals to mass over volume. Of course, that's our formula for calculating density. Okay, but then the material here that we are talking about is in the form of a cylinder, right? And we know that the formula for calculating the volume of a cylinder is the base area of a cylinder times the height. And we know that the base of a cylinder is circular, right? So that the volume of a cylinder is equal to pi r square height, right? Pi r square h, right? So we just substitute the values that are given to us according to the question. Of course, we know that pi is 22/7. Okay, then times the radius here is 0.1. Okay, but in our formula the r is squared, so we are going to square that value. So that's what I have, 0.10 squared, then times the height, which according to the question is 0.5. So we have 0.5 here, right? Now remember that density is equal to mass over volume, right? and the value of the mass given to us is 44 grams. So we just substitute those values into our formulas. So that we'll be having 44, which represents the mass of the cylinder, all over the volume of the cylinder, so which cover all this, right? And we know that the formula for calculating the volume of a cylinder is pi r square h, right? Now, if we take the square of 0.10, that will be equals to 0.01, right? So this 0.01 is also equal to 1 over 100, all right? If I'm having 0.01, this is also equal to 1 over 100, right? So what I basically did here was to move the 100 upward, more or less like we're having two-step fraction. So the denominator of the second fraction was moved upward, right? So that we'll be having 44 times 7, okay, times 100 times 10, okay? Because here, this is also the same thing as 0.50 is also the same thing as 0.5, right? So 0.5 is also equivalent, or it's also equal to it's also equal to 5 over 10. So the 10 too was also moved to join the numerator of the main fraction. So that we'll be having 44 times 7 times 100 from the 1 here, okay, times 10 from the 0.5. So that we'll be having 22 times 5 left as the denominator of the fraction. Of course, 22 here is 1, 22 here is 2, 5 here is 1, 5 here is 2. 2 times 2 is 4, right? Then 4 times 7 is 28. Then 28 times 100 is equals to 2,800, okay? Okay, so that the density of the material of the drum is equals to 2,800 kilogram per meter cube, right? So from the table, from the previous table, you find out that this is very close to the density of aluminium, which is about 2.7, of course, times 10 raised to power 3, okay, in kilogram per meter cube. So we can say the material, okay, of the drum is probably made from aluminium. Okay, so let's move to the next slide. So let's take example 2. The relative density of an alloy is 6.5. So an alloy is just a mixture of 2 or more metals, okay? So the relative density of an alloy is 6.5. A, find the mass of a solid alloy cube of side 20 centimeter. B, what volume of the alloy has a mass of 13 kilogram, right? So we know that the formula for calculating density is equals to mass over volume, right? But if you look at the question carefully, we are not given density, okay? But from the relative density, we can actually get the value of the density, right? And we know that the difference between relative density and density is just the unit. So one has unit and one doesn't have unit, okay? So in this case, relative density doesn't have unit, but density has unit, right? So since our mass is given to us in kilogram, right, given to us in kg, then our density should also be should carry that kg, right? So for us to get the value of the density from the relative density, we just multiply by 1000, so that our density will be in kilogram per meter cube, right? And we know that the formula for calculating the volume of a cuboid is just the length, or the size of the length cube, right, which is length times length times length, right? So all being said, volume of a cube is equals to length times length times length, right? So that will be equals to 20 times 20 times 20 all over 100 cube. Now remember that we are given the side of the cube in centimeter, so we have to convert it to meter, right? And to convert this, and to convert 20 centimeter to meter, we have to divide by 100, right? Now since we have 3 values, okay, since we have 3 values, so we have to divide by 100 raised to power 3, right, in order to convert it to meter. Now mass therefore is equals to the density that is given to us, right, then times 20 times 20 times 20 all over 100 cube. And remember that 100 cube, according to the law of indices, is also equal to 1 times 10 raised to power 6, right? So that we'll be having 52 times 10 raised to power 6 all over 10 raised to power 6. Okay, so how did we get that 10 raised to power 6? Now, if you count this 1, 2, 3, 4, 5, we're having 5 zeros, and here we're having 6 zeros. We can easily cancel that. Or just to multiply the side of the cube, which is 20 times 20 times 20 times 6,500, right? So that will be equals to 52 times 10 raised to power 6, right, divided by 10 raised to power 6. So according to the law of India 6, this is the same thing as say 1 times 10 raised to power 6, right? And 1 times 10 raised to power 6 is still the same as 10 raised to power 6. But remember that this is not in standard form. Okay, take note of that. So 10 raised to power 6 can cancel out 10 raised to power 6, so that we'll be having 52 left. Therefore, the mass of the cube is equals to 52 kg, right? So that is the answer to A. Now for B, we are asked what volume of the alloy has a mass of 13 kg. So in this case, we already know the mass, right? And we already know the density. The density of the alloy still remains the same, so we are looking for the volume. So from the formula of density, we can easily make V the subject of formula by cross multiplying or by interchanging the position of the density and that of the volume. So volume will leave here and replace density here, while density will replace volume here, so that V is now equals to mass over density. Okay, but remember that the mass given to us is 13 kg and our density still remains the same, 6,500 kilogram per meter cube. So that volume is equals to 13 over 6,500, right? 6,500. 13 here is 1, while 13 into 6,500 is equals to 500. So that we'll be having 1 over 500, right? And 1 divided by 500 is equals to 2 times 10 raised to power minus 3 meter cube. Okay, so the volume of the alloy when the mass is 13 kg is equals to 2 times 10 raised to power minus 3 meter cube. So let's move to the next slide. Right, so here we are going to be discussing about irregular solids. So irregular solids are those solids that we cannot give a name to their shape. Okay, we cannot give a name to their shape. More or less like they are composite shapes. Right, so we cannot give a specific name to their shape. So how do we find the mass of such shapes, and how do we find their volume? Okay, so that is what we are going to be discussing here. So the mass of an irregular solid body can be obtained by direct weighing, right? While the volume can be found by immersing the body in water, provided it will sink and that it is not soluble in water. That means it does not dissolve in that water. Okay, so the volume of water display will be equal to the volume of the solid, right? So to perform that experiment, we simply need a measuring cylinder or an overflow. Okay, that is what we use in determining the volume of the liquid display. So the figure below, okay, the figure below illustrates what I have just described above, right? So this is a measuring cylinder, and this is the initial volume of water before the solid, okay, was dropped inside. So when the solid was released and dropped inside, the volume of water increased, right? So you just measure the difference between the original volume of the water and the new volume of water, and the difference between them is equal to the volume of the solid, or you can as well use an overflow. Okay, so this is what is referred to as an overflow. So once you drop the solid inside, right, the water will be displayed. So that display water will flow through the nozzle, right? We flow through the nozzle into the measuring cylinder, where you can easily read off the volume of the water display, right? And the volume of the water display equals the volume of the solid. Okay, so this is just how we determine the volume of an irregular shaped solid. Let's move to the next slide. So on the next slide, we are going to be discussing about relative density of liquid by direct method. So by direct method, of course, we have relative density bottle. So we are going to be here, we'll just be discussing how to use the relative density bottle to measure the density of a liquid. Okay, and that is what is referred to as relative density of liquid by direct method, because we are using a relative density bottle to measure the density of the liquid directly. Okay, so the simple step is that the relative density bottle is weighed empty. Okay, first of all, you weigh the relative density bottle empty, and its mass, we call it M. Okay, then the next step is to fill it with liquid and weigh it. Okay, and the mass, we call it M1. Then finally, you empty the relative density bottle, dry it, and refill it with water and weigh it again. Right? So in that case, we call it M2. Let's move to the next slide. So in that case, we call it M2. Now, we know that relative density is equals to density of liquid all over density of water, right? Which is also equals to mass of liquid all over mass of equal volume of water. So from the experiment we perform above, the mass of the liquid will be the mass of the relative density plus the mass of the liquid, then minus the mass of the empty relative density bottle, which is M, right? So that will give us the mass of liquid, while the mass of an equal volume of water will be equals to the mass of water plus the mass of the relative density, then minus the mass of the relative density when it is empty, right? So we are going to be solving some examples where we are going to be putting these formulas into work. So let's start with example 1. An empty relative density bottle weighs 25 grams. It weighs 65 grams when filled with a liquid and 75 grams when filled with water. Calculate the density of the liquid. So we are going to move over to the board to solve this question. Okay? So let's first of all, the first thing first is let's know what we are asked to do in the question. Okay, so we are asked to find the density of the liquid, right? But from the information given to us, what we can do first is to find the relative density, okay, of the liquid. Then from the relative density of the liquid, then we can now get the density of the liquid. So in this case, relative density of liquid will be equals to mass of liquid, right, over mass of equal volume, okay, of water, right? So let's just pick out some information that are given to us. So the relative density bottle when it is empty, so let's call it arrow, okay, dB, right? So this is the mass of the relative density bottle. They said it weighs 25 grams, right? So when it is filled with liquid, so let's call it arrow.dl. So this is when it is filled with liquid. It weighs 65 grams, okay? Then when it is filled with water, so let's call it arrow.dw, right? That is 75 grams. Okay, so from the information given to us, we can calculate the relative density of the liquid. So this will be equals to, right? So this will be equals to 65 minus 25 over 75 minus 25. Of course, the 25 here represents the empty relative density bottle, right? While the 65 here represents the mass of the relative density bottle when it is filled with liquid, okay? While the 75 here represents the mass of the relative density bottle plus water, right? Okay, so if we subtract 65 from 25, that will be equals to 40, right? That will be equals to 40. If we subtract 25 from 75, and that will be equals to 50, right? So 0 we cancel 0. So that 5 into 4 is 0, then point, then put a point in front of the 4 so that the 4 becomes 40, right? So 5 into 40, that will be 8, okay? So in this case, the relative density of the liquid, okay, the relative density of the liquid is equals to 0.8. Now take note, we are not asked to calculate the relative density of the liquid, we are asked to calculate the density of the liquid. So the density of the liquid, okay, the density of the liquid will now be equals to 0.8 grams per centimeter cube, or right 800 kilogram per meter cube, right? So this is the value of the density of the liquid. So let's move over to the screen. So this is where we draw the curtain for the preview for today's video. Okay, you can enjoy the complete video by clicking on the link in the description below, and that will take you to my school website. There you have to subscribe to enjoy the complete video. And in the complete video, we still solve more problems on relative density. We now went further and discuss about Archimedes' principle, and we also discuss about the principle of flotation and many more. Okay, so I believe you enjoyed this little one that you have watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.